So, hello students, welcome back again. Let's continue the discussions to develop some continuous functions for our nodal variables, and in that context we have the Rayleigh-Ritz procedure. I will introduce you to this procedure. It's a beautiful way of expressing the continuity of the nodal variables, and in fact this is a precursor to the current finite element analysis based on the numerical methods, where the Rayleigh-Ritz method is a mathematical one, and later with the advent of digital computers, the entire thing is digitized. And let's see, and before we go into the Rayleigh-Ritz procedure, let us see what we did in the previous lectures. Okay. So, in the previous lectures we had seen we have defined the conservative system, and the conservative system is where in which the work done is independent of the path taken by the load. It is only based on the distance between the 2 points, the least distance between the 2 points, and we have seen the application of virtual work and stationary potential energy methods for solution of some simple problems, both one-dimensional and two-dimensional, and we got the solutions in discrete form in terms of nodal degrees of freedom. We got a solution, but these displacements are only particular to the nodes that we have, and the solutions that we had obtained both by the stiffness method and also by the energy methods, we found that they are one and the same. It is because both are solving the same equations, and then as I mentioned earlier, all these solutions were obtained at discrete points, and our next target should be to get a continuous variation, because we want to move into continuum, because our object is to determine the response of soil as a medium. The soil is a continuous medium, unlike your bar and beam element and the spring elements. So that we will do in this today's class. And before that, just let me recap our total potential energy of the system. And although the concept is applicable universally for one-dimensional, two-dimensional and three-dimensional and continuum, discrete and all types of systems, we had only seen it in the context of uniaxial elements in yesterday's class. Okay. We write the total potential energy of the system pi as u plus omega, where u is the strain energy of the system. See here, what we mean by the system is, we have a spring and then there is a load P, and the P is the applied load, whereas the spring is the system that we have and that can store the energy. Like if we elongate or compress, it can store the energy. And so if you gradually apply a displacement of delta, the average force multiplied by displacement is the energy, because to start with delta was 0, so the spring is not loaded, so there is no energy in the system, but as you are gradually elongating or compressing it, it is developing some force and then it is developing some energy, that is force times displacement. So the average force is 1/2 k delta multiplied by your displacement, that is 1/2 k delta square, and then the omega is the loss of potential of the external load. It is actually by moving the load by that much, it is losing the potential to do the work. Before the application of this deformation, the load has so much potential to move, but out of that we have taken out some delta, and that minus P delta corresponds to the loss of potential of the external load. So, we write it as minus P delta, So our total potential is 1/2 k delta square minus p delta, and our stationarity principle states that any small variation in this total potential should be equal to 0 for the system to be in equilibrium, and that we had seen yesterday with the example of a marble moving in a pan, and at the top of the pan the marble has a chance to roll down, but then at the bottom of the pan the marble is stable, and even if you slightly deform or move it a little bit, it is still stable because it is at the bottommost point within the pan. Okay, that is what we mean by the constant potential energy. And now this is in a discrete form. See, we have a delta that is known at one point, and the energy is defined in terms of that. But then what happens inside, like let us say you take some other point here, we do not know, and so it is good to go in for continuous forms of the same equation, so that we can apply this method to a continuum. And before that, see, Rayleigh-Ritz procedure, let me introduce the Rayleigh-Ritz procedure. And in 1870, Lord Rayleigh, he introduced this concept for vibration problems for determining the eigenvalues and eigenvectors, and Ritz in 1909, he also proposed a similar methodology, and combining both these names, this Rayleigh-Ritz procedure is developed. And they suggested that we can assume the solution in a polynomial series, right? And let us say u is our variable, u is let us say displacement, and if it is a one-dimensional problem, there is only one coordinate x, and you can assume any polynomial like a0 plus a1x plus a2x square plus a3x cube and so on, like it could be an infinite series of series. Okay. And in 2 dimensions we will have 2 coordinates x and y, and the polynomial could be a0 plus a1x plus a2y plus a3xy plus so on, like we can have any number of terms. And in 3-dimensional problems, u of x, y, z, this could be a0 plus a1x plus a2y plus a3z and so on. Okay. And what they said is these a's, a0, a1, a2, a3 and so on, these are the degrees of freedom that need to be determined to find the solution. So actually previously we defined the degrees of freedom at the node points in x direction and y direction, and similar to that the Rayleigh and Ritz, they called these a's as the degrees of freedom or the generalized coordinates that we will see later in the context of finite element analysis. And what they also said, this assumed polynomial should meet some requirements, and the first thing is the polynomial should be admissible, and that is it should satisfy all the essential boundary conditions and then satisfy the compatibility conditions. So, it is actually there should not be any break in the shape of the element or break in the variation. So, it should be basically it is a continuous function. Okay. And so these boundary conditions, the simplest ones are essential boundary conditions or geometric boundary conditions. Let us say we take a cantilever beam, a fixed end cantilever beam, and we can say that at this fixed end your displacement is 0 and then the slope is also 0, and these are the minimum boundary conditions that any solution should satisfy, so that we get some reasonable result. It may not be accurate, but at least it should be able to represent this boundary condition of this fixed end. So, the beam displacement W is 0 is one boundary condition, and then the slope dou W by dou X is also 0. And apart from this, we may have some non-essential boundary conditions. That is, let's say if you look at this beam, we have applied a tip load, and within this beam your shear force should be constant. It is just simply P, and then your bending moment should be 0 at the tip because there is no lever arm for this load. Then the bending moment should be maximum at this point, at the fixed end point, that should be equal to P times L. Okay? And these are something that we don't enforce, but we need to get out of the solution. So, our bending moment is EI dou square W by dou X square is 0. EI times curvature is your moment, and it should be 0 at the tip, that at X is equal to L. Okay? And if our solution is admissible, it will satisfy the essential boundary conditions, and it may or may not satisfy the non-essential boundary conditions, like your shear force is constant along the length, or your bending moment is 0 at the tip, and so on. Okay? And if the solution is exact, it will satisfy not only the essential boundary conditions, but also non-essential, like for example, your shear force is constant and the bending moment is 0 at the tip. Okay, these non-essential boundary conditions are problem dependent. This is whatever I explained is only in the context of the cantilever beam, and there could be something else for different problems. Now, let us look at this potential energy equation in a continuous form, and let us apply this for an axial element, and from now on our object is to get the solution in a continuous form, like whatever may be the point, we should have a solution, unlike in the case of the previous examples where we defined the degrees of freedom only at some discrete points, but now we want a continuous function, and we have an axial element, and it may have some strain and then some stresses. The strain and stresses are proportional to each other, and it may be subjected to its own self weight, and then on top of that there could be some external loading, and it is an axial element, so there is only one direction. Okay, and let us say that it is of length L, and so there could be some potential energy because of the internal strain. See, the strain is if U is the displacement, axial displacement field within the element, dou U by dou X is the strain, and our Young's modulus times strain is the stress, and the stress multiplied by strain is the work done. Okay? And we can integrate this over the full length of L, and we are taking the average stress, so that is 1/2 E times dou U by dou X, okay, multiplied by the strain dou U by dou X, and then we have an area, cross sectional area A, and we integrate this over the length of L, we will get the potential energy of the system. Okay, and this A could be anything, it need not be constant, because now we have an integral equation. We can have a bar with a variable cross section, so it may be varying along the length. So, in that case we can put an A of x and then define some function, okay. And then the loss of potential because of the self weight. So, if U is your axial displacement field within the element, gamma times dx times A is the force, right, at any point. That multiplied by the displacement at that point is the work done. And then because we have a length, and this unit weight is acting over the length of the element. So, it is 0 to integrated over 0 to L. So, gamma times A cross sectional area multiplied by dx is the force multiplied by displacement at that particular point u, okay, and we integrate this over a length of L. Then on top of that, there could be some externally applied forces along the length of the bar, and let us say that vector is P, Pi. Pi is the load at location 1, location I, multiplied by the corresponding displacement ui, right. And so, this we can equate, like if your area of cross section is constant along the length, we can bring it out of the integral Ae by 2 integral 0 to L epsilon x square. Epsilon x is nothing but dou u by dou x, and here we are assuming that our displacements and the strains are so small that our strains can be the first order variation of your displacements, okay, dou u by dou x. The rate of change of displacement is called as the strain, okay, and minus gamma A integral u dx minus of the sum total of ui and pi, okay, and this is our total potential energy of the system. And what Rayleigh and Ritz have proposed is that we can assume u in terms of some polynomial expansion as a0 plus a1x plus a2y and so on, and our a0, a1, a2 and so on, these are the degrees of freedom that are similar to our previous degrees of freedom. Then any variation in this total potential with respect to any of these degrees of freedom should be 0 for the system to be in equilibrium. And so, what we do is we can assume some solution in terms of a polynomial, and then work out this total potential and then determine the constants a0, a1, a2 and so on. Okay. So, let us as an example illustration, let us take a bar, okay, and it is applied a load of P at the tip, and this bar is of length L, and previously we had defined these bars with some certain nodes, node 1, node 2 and so on, but here we do not have any such notation. This is just a simple bar, it is a continuous bar of length L. Then at the tip there is a load of P applied, okay, and we want to find a solution for this, and let us say that our solution is to start with u of x is a0 plus a1x, right. It is just a simple assumption, like you can assume anything you want. You can assume a0 plus a1x plus a2x square and so on, and to start with I have assumed this, and our boundary condition is that at x is equal to 0 our displacement is 0 because this is a fixed end. So, our u is 0 at x is 0, so that means that a0 is 0. So, u of x is a1x, and this is called as an admissible solution because it is already automatically applied the required boundary condition, okay. And instead of 0, let us say we put some constraint that the tip the displacement at this end is some delta, that a0 could be equal to delta, right, and the strain within the element is dou u by dou x, and that is equal to a1, okay, and our total potential pi is integral 0 to L 1/2 ae dou u by dou x times dou u by dou x. It is actually basically 1/2 ae times epsilon x square and minus of ui pi, okay, and if you integrate this you substitute u of x here and integrate, you get 1/2 ae a1 square, because we have dou u by dou x times dou u by dou x, and then L, okay, because the strain does not have any x, we just have an L, and the displacement at the tip is a1 times L multiplied by the load at that point P, right? And if you apply the stationarity principle, dou pi by dou a1 should be 0 for our equilibrium, and so if you differentiate with respect to a1, we get ae times a1L minus Lp, that is 0. So our a1 is p by ae and our u is px by ae, right? And then at the tip, the displacement is PL by AE, that is our familiar equation from the strength of materials. And how do we know that this is an exact solution? So for that, we can determine the strain dou u by dou x, and if you do that, that comes to P by AE. P by A is the stress, and divided by E is your strain, and that is constant along the length. And we know that if you apply a tip load, the displacement at the tip is PL by AE and the strain is constant. So we can say that this polynomial that we had assumed for the displacement is will give us exact solution for the tip loaded problem. Okay. And now let us look at some other problem. Okay. Let us say that we have a bar of length L, and then it is subjected to its own self weight. So it is hung from the ceiling like this, right? And then because of its own self weight, it will elongate, and we want to get the displacement field under this self weight. And so let's see that minimum conditions that we have are the displacement at this point is 0, and then along the length our strain is going to vary linearly, right? Then at this point, at this tip, we know that the strain is 0 because that the free end, and there cannot be any strain associated with this, right? And at this point the strain should be the maximum, right? And then we do not know what is your tip displacement, that we can easily determine. Okay, let me just try this. Okay, let's say we take any arbitrary length of dx, okay, and our weight, our weight is gamma times a times dx, right? And our d delta is actually, it is let us say dw. D delta is dw by a times x. Let us say this is at some distance x from the origin, okay, and so we have this as d delta right, we should have a Young's modulus E, okay, that is the stress divided by E times x, okay. So gamma dx times x by E, okay, and our delta is we can integrate from 0 to L gamma by Ex dx, that comes to gamma L square by 2E. Okay. This is what we can easily derive theoretically, and let us see what happens with our solution. Okay. let us let me go back to my laser. Let us assume a first order polynomial. Let us say u is a0 plus a1x, and at x is equal to 0, our a0 is 0, and so our u is 0, so a0 is 0, and so our u of x is a1x, and the strain is dou u by dou x, that is a1, and we see that we can say at this stage itself that this polynomial is not sufficient because our strain is constant, but then because of the increasing weight, your strain is going to vary linearly with the distance. But let's do the problem and then find out later. But at this stage itself, even at the time of assuming the polynomial itself, we can say that our solution is not going to be accurate. Okay? So, our total potential pi is integral 0 to L 1 half AE epsilon x square dx minus gamma A dx, that is the force, multiplied by u, integrated over 0 to L, that is the total loss of potential. And if you integrate, if you substitute your EU as a1x and integrate, we get 1 half AE a1 square L minus gamma a1 L square by 2, right. And so we can apply the principle of the stationarity, and dou pi by dou a1 should be 0, and if you go through this integral, we get our a1 is gamma L by 2e, okay, and our displacement at any point is gamma L x by 2e, right, and our displacement at the tip, if you substitute x is equal to L, the displacement at the tip u is gamma L square by 2e, and if you just look at this result, it looks accurate. That is what the theoretical result is also gamma L square by 2e. So, our tip displacement is also exactly matching with the exact result. So, can we say that the solution is accurate? But then we have to look at other things, like we can evaluate the displacement at some other point and see. And so, let us go for higher order term, that is dou u by dou x, and so if you do this, gamma L by 2e, and that is constant, that is coming out as constant. Actually here itself we could have seen that the strain is constant A1, okay, and we know that the strain should vary linearly, but then our solution is saying that the strain is constant. So, that means that whatever solution that we have obtained is not sufficient, it is admissible, like because it is satisfying the boundary conditions, but then it is not sufficiently accurate. We need to improvise it, and let me just now let us include one more term in the polynomial and see what happens. Now we are saying u is a1x plus a2x square. We have added one more polynomial term, and our strain is epsilon x is dou u by dou x, that is a1 plus 2a2x, and our pi is integral 0 to L 1 half AE dou u by dou x and dou u by dou x minus integral 0 to L gamma A u dx. And if you do the integration and then set up two simultaneous equations by taking dou pi by dou a1 and dou pi by dou a2 to 0 and set them to 0, and then solve, we will see that a1 is gamma L by E and a2 is minus gamma by 2e. Okay, these are the two constants that we determine. So, our solution u is a1x plus a2x square, and A1 is gamma L by E. So, our solution U is gamma L by E x minus gamma by 2E x square, right. So, if you substitute x is equal to L, our tip displacement comes out as gamma L square by 2E, which is equal to the exact theoretical result. But then before we conclude whether it is good or bad, our strain along the length is dou U by dou x, and that comes out as gamma L by E minus gamma x by E, right. So, our strain is going to change along the length, and at the free end, let us look at the free end at x is equal to L. If you substitute, your strain comes out as 0. That is what we have, and then at x is equal to 0, your strain is gamma L by E. Gamma L is the total stress, and divided because of the total length of the element, okay, and divided by E is your strain, okay. And so basically, if you plot, your strain variation will come out like this. So, our strain is maximum at the top, and then it is decreasing to 0. Okay, let us say this is 0, and here it is gamma L by E, and that is natural because we can easily see the variation, because as you are moving along the length, your stress is changing. The stress is maximum here, gamma times L, and the stress is 0 here, okay. And so, our strain is 0 here and gamma L by E. So, that means that whatever solution that we got, this is our solution. This is exact solution, okay. So, we can conclude that this is it, like we do not need to increase any further, this polynomial need not be changed any further, and we can stop at this polynomial. Let me just see. I think I am getting better at writing, because if you write anything at one shot, it will get erased easily. Okay. Now, let us move on to other problem. Like let us go on to the flexural problem, okay, beam element, and let us consider a beam element like this, and let us neglect axial displacements, because axial we have already done with the bar elements, with the axial elements, and let us also assume that it is a pure flexural element, and there will not be any shear induced bending, okay, and shear deformations are neglected, and we can write our total potential energy equation as integral 1/2 EI dou square W by dou x square whole square. Actually, dou square W by dou x square is the curvature, and your moment times the EI times this curvature is your moment, and the moment times curvature in the integral form is the work done, right, and integral of curvature is your theta, that is the rotation, and so this is your integral expression for the work done by the moment and then the rotation, okay. And let us say that W is the transverse deformation, and let us have some applied force Q that is varying along the length, and let there be some shear forces applied along the length, and then some moments, and we can calculate the loss of potential corresponding to these like this. Let us say our Q is a continuous function, and this could continue over the full length 0 to L, okay, W times Q dx, okay, where W is our transverse displacement and Q is the traction. And then say at this point your displacement is W1, the loss of potential is F1 times W1, and corresponding to F2, let us say the displacement is W2, so the loss of potential is F2 times W2. Similarly, the loss of potential because of the rotation and the moment is theta times m at some discrete point I, right? And our W's are the transverse displacements at discrete points like point 1, point 2, point 3 and so on. And our W of x is the deflection of the beam as a function of length L x, okay? And theta of x is the rotation of beam as a function of x, and Fi is the externally applied shear force at some discrete points, and Mi is the externally applied moments at discrete points, and Q is the applied traction. It's a surface force or surface pressure, okay? And this is your total potential of the flexural element. This is coming from the internal moment, and then the rotation integral curvature is rotation, okay? And so we can actually apply this total potential energy equation and then get some limit solutions for simple problems as a demonstration, but it is applicable for any problem, any let's say even if you have a building frame, you should be able to solve it using this methodology, okay? Let's apply for a simple problem of cantilever beam with a tip load, okay? And since we do not have this Q and other things, we can write the total potential as 1/2 EI dou square W by dou x square, the whole square integrated over 0 to L minus P times the tip displacement, okay? And what is the polynomial that we can assume? See, this polynomial can be in the form of A0 plus A1x plus A2x square plus A3x cube and so on. But the essential boundary conditions are at x is equal to 0, our displacement is 0, and then our rotation is 0. The slope should be 0 at this point. So, if you do that, W is 0 at x is equal to 0 means A0 is 0, and dou W by dou x is 0 at x is equal to 0 means A1 is 0. So, our admissible polynomial can start with A2 x square and so on, okay? And let's assume only a single term just for simplicity, and let's say that our W is A2 x square, okay? And we can see how good the solution is with just single term, okay? And dou square W by dou x square is 2A2, and dou square W by dou x square whole square is 4A2 square, and we can substitute these terms dou square W by dou x square and then W of L in this equation, and then the total potential energy is this, and then variation with respect to A2 should be 0. So, that means that our A2 is PL by 4EI, and we can substitute that back here. So, our W is PL by 4EI times x square, okay? And so, our W of x is PL x square by 4EI. So, at x is equal to L, our W is PL cube by 4EI, which is not correct because our displacement, tip displacement is PL cube by 3EI, and so actually if you look at this solution, W of x is PL x square by 4 EI. Your the shear force should be constant with within the beam section, and that is not coming out, and EI dou cube W by dou x cube is actually, it is coming out as 0, which is not correct. Sorry, I think it should be only PL by 2 only. And dou square W by dou x square is x gets disappeared, and your bending moment should be 0 at x is equal to L, and that's not coming out, and your bending moment should be increasing linearly along the length. So in fact, at the fixed end it should be P times L, which is not coming. Like your bending moment is constant, and then the shear force is 0. So that means that this polynomial is not able to give us the required solution, and we can try to improve the solution by assuming a higher order polynomial a3x cube, and once again we see that our solution is not good enough, because we are not able to get a constant shear force, and then the bending moment is not 0 at the tip, and it's not equal to P times L at this fixed end. Okay, so now we can actually try another thing. Let's include the two polynomial terms, one quadratic term and one cubic term, a2x square plus a3x cube. And inherently we also have a0 and a1x, but only thing is a0 and a1 are 0. Okay, but we can technically say that we have those terms also in this polynomial. Okay, so dou w by dou x is 2a2x plus 3a3x square, and dou square w by dou x square is 2a2 plus 6a3x, and the whole square of that is this, and so our total potential of the system is this, and we can differentiate this with respect to a2 and a3 and set them to 0 and find our constants. So if you go through this, your a2 comes out as PL by 2 EI, and a3 is minus P by 6 EI. So our so if you substitute these two constants a2 and a3 in our equation for w, w is PL by 2 EI x square minus P by 6 EI x cube. So if you substitute x is equal to L, your w is PL cube by 2 EI minus PL cube by 6 EI, that is PL cube by 3 EI, which is the same as what we get from the flexural theory. And let's calculate the bending moment at the tip of the beam. Dou square w by dou x square at x is equal to L is PL by EI minus Px by EI. Okay, and if you substitute x is equal to L, that is 0. So at x is equal to L, it's 0, and then at x is equal to 0, your bending moment is PL. Okay, because actually it is EI times dou square w by dou x square. Then as you are moving inside, your bending moment is going to increase. Okay, and then shear force within the beam is EI dou cube w by dou x cube, that comes out as minus P, and that is constant along the length, right? So so we see that considering two terms a2 x square plus a3 x cube is able to give us the exact solution. It is predicting the tip displacement correctly, then it is giving us the constant shear force, and then bending moment of 0 at the tip, and then bending moment of p times L at x is equal to L. So, we can say that this polynomial is able to satisfy both essential and non-essential boundary conditions, and so it must be exact. And what is the difference between the earlier polynomials and this polynomial? Actually, earlier we had considered only one term, a2x square or a3x cube, and then with a2x square our solution was not correct because this polynomial order was not sufficient. But then if you assume x cube term by neglecting the lower order term, also we have a problem. We had, in fact, the solution has become worse. Now it is PL cube by 12EI. Previously it was PL cube by 4EI, which is at least close enough to PL cube by 3EI, but now the solution has become even worse, and our bending moment and the shear force are not what we expect. Okay? And so the reason for this is we are not including the complete polynomial, and what Rayleigh and Ritz have suggested is you include a complete polynomial for any problem to improve the solution accuracy. Okay? And so by including this, and in fact this is a complete polynomial because this is also including a0 plus a1x, but only thing is a0 and a1 are 0, so we do not see those terms here. So we have a cubic polynomial, complete polynomial, and we are able to get the exact solution. And let us say that we assume one more term, a4 x to the power 4, because let us say we are not sure of the solution that we get with the previous polynomial, and if we assume one more term and continue, what will happen? So actually the solution is a bit more tedious because now we have three simultaneous equations to solve for three unknowns, a2, a3 and a4. Okay? It is a very tedious problem, but then if you do that, you will see that our a4 will come out as 0, because already the solution is accurate or exact with these two terms, a2x square and a3x cube. Okay, I will not do it here, but you can try it out on your own. It takes a long time. It might take about 2 hours if you do it systematically, and then you will find that a4 is 0. And so if you have access to any of the programs like MATLAB, you can set it up in the MATLAB program and then do all these problems, like you can solve simultaneous equations in a symbolic form. Okay? Because in a calculator you can only solve in numerical form, but in MATLAB you can do it in the symbolic form and get your a2, a3, a4 and so on, whatever may be the equation that you have. Okay? So the lesson that we have to learn is when we assume any polynomial, it should be complete, and it should include all the lower order terms for better accuracy. So when we had a2x square, the solution was more accurate compared to the solution that we got with a3x cube as the single term, because a2x square had included the two other lower order terms, the constant and then the linear term. Okay? And but when we included the cubic term, we have neglected the square term, the quadratic term. So the solution, the accuracy has come down. Okay? So now let's do one more term, one more polynomial, and then see what happens. Let's assume w of x is a3x cube plus a4x to the power 4, and we have neglected the x square term. Okay? Then if we go through the solution that we get is this, and the solution really does not match any of the theoretical solution. Then it does not give us the required boundary conditions and the higher order derivatives, like our shear force should be constant along the beam at P, and your bending moment is 0 at the tip. That does not happen. So you can the solution is given, and you can see that at the tip the displacement does not match your equation PLQ by 3I, okay? And then along the length your shear force is not constant, okay? So, and this procedure can be continued for other problems, like let us say you have a cantilever beam with a loading at some other point, not at the tip but somewhere else, or let us say you have a simply supported beam with a central load, and we can apply it for any problem, but only thing is we do not know how many terms, polynomial terms we need to include. Okay, previously for the tip loaded problem, our solution with the two polynomial terms were exact, a2x square plus a3x cube, and let us see whether this will work out for this problem of the cantilever beam with a load applied at the midpoint L by 2. So, if you do this, your solution is coming out as 3PL cube, 3PL by 16EI x square minus P by 12EI x cube. And so, actually see, when we do this problem, beyond this length of L by 2, your bending moment should be 0 beyond this length, but our solution that we get does not give that, okay? And so that means that we need to include one more polynomial term and redo the problem, and we can continue until we get the solution that satisfies both essential and non-essential boundary conditions. But beforehand we cannot say how many terms we need, okay? And this is the problem with a uniformly distributed load. The potential equation is Q times W integral 0 to L, because your Q is varying along the, or it is continuing along the length, okay? And if you have a simply supported beam, the essential boundary conditions are the displacement is 0 at both the ends, at x is equal to 0 and x is equal to L. We need to enforce that apart from all the other required boundary conditions. And let us do one more thing, like let us look at the potential equation for a 3-dimensional continuum. It is for a continuum, and a continuum is characterized by different stresses, sigma x, sigma y, tau xy, and then sigma z, tau xz, and tau yz, and so on. And let us say that our continuum has got some strain vector epsilon, and say if D is the constitutive matrix, D times epsilon is the stress, and that multiplied by strain is your work done, and half, because the average stress is half D epsilon, okay? That multiplied by your epsilon is your strain, and integrated over the full volume. Now, since we have a continuum, we are integrating over the volume, okay? And then say if your epsilon naught is the pre-existing strain, and the current stress epsilon transpose D times epsilon naught is your work done because of your initial strains and then the stresses, and there could be some initial stresses also, and then say if your B is your body force vector and u is your displacement vector, internal displacement vector. You can write this loss of potential as u transpose b dv, okay. And then you may have surface traction, and where our u is the surface displacements, t is the surface traction, and this integrated over the surface area s, whereas the others are integrated over the volume. And on top of this, you may have some discrete loads, concentrated loads at different points, and the work done is AE transpose times P, where AE is your vector of displacements, P is the vector of applied loads. So, the potential equation for a 3D continuum is a bit more complicated, and so this is our object. Like we will move on to the continuum from the next class onwards. So, what we have seen in this lecture is by following the Rayleigh-Ritz procedure, we can obtain solution in a continuous form. We do not need to discretize our mesh into certain number of nodal points and get our solution, but by applying this, we get a continuous solution, and we can assume some polynomial, and that polynomial should be admissible at the minimum, and the admissible polynomial will satisfy the boundary conditions, and if it is going to be exact, it should satisfy even the required boundary conditions and higher order derivatives like your bending moment and shear force. Okay. And see, these you should remember that we are not solving for bending moment and shear force, we are only solving for displacements, and from the displacements we are getting your bending moment and shear force as EI times dou square W by dou x square, and EI dou cube W by dou x cube. Okay. And then the same procedure we can continue for a 3D continuum, and this we will see later in a slightly different form, not in the potential equation form, but in the virtual work form. Okay. So, that is my last slide. So, I hope you understood the Rayleigh-Ritz procedure. It's a very beautiful procedure, and it's more mathematical, but it has got some relevance to what we are going to do in finite element analysis, because even here we assume some polynomial, and depending on the type of polynomial that we assume, our solutions might be totally different. Okay. So, if you have any questions, you please write an email to this address profkrg@gmail.com, and then I will be able to respond back to you. So, thank you very much.